our last time, we introduced you to these guys called space curves, which are essentially just pathways in 3D space, right? We're interested in space curves in 3D, and here are a list of the things we're going to do from section 13.1. We're going to find the limit of a space curve. So what's the limit of a function as x tends to 0? We're going to look at what's the limit of a space curve as t tends to 0. And we're going to look at what's the domain of a space curve, because essentially it is a function. Even though it's a vector function, it's still a function. The third one, we're going to just basically jump to GeoGebra and do some sketches of them. That should be nice and fun. Then the fourth thing we're going to do is show you how you can find the equation of a space curve. And the last thing we're going to do, hopefully we'll get to it, I don't know if we will, we're going to find out the point or points where a space curve intersects a plane or another space curve. So can you imagine a plane like a surface, a hill, and you've got a space curve? It could pop in, you know, hit the thing, zoom about inside, and then pop out again. So there might be two places where it intersects. You could have a space curve and a second space curve, like two jets flying. They could crash into each other. That would be a point of intersection. In fact, if they don't, the analogy of planes doesn't work here, but if they intersect, could they curve round and intersect again later on? So that there might be more than one point where a space curve intersects with another space curve or with a plane. And that's kind of the list of things we're going to do. Some of these things are quite analogous to what you would have done way back in 141 or in Calc 1. So let's look at the first kinds of questions. And these are questions similar to 1, 2, and 3 in your homework. That's what that's about. And we're going to look at how do you find the limit of a space curve at a given point. So it might look something like this. Find the limit as t tends to 0. And the space curve is going to be called e to the t. Two t over sine t. And tan of t. Now, on Wednesday, we kind of, when we introduced space curves, we showed you that if you want to differentiate a space curve, don't you just differentiate each piece? I know that's not in the list, but that's what actually 13.2 is going to be about. So you will get to do it. And if you want to integrate a space curve, don't you just integrate things? So if you keep that thought in your head, if I wanted to find the limit of this space curve, does it seem sensible that I just find the limit of each piece as t tends to 0? In other words, you do 3 baby limits, and that's exactly what you do. So we're going to find the limit as t tends to 0 of that guy. And then we're going to find the limit as t tends to 0 of this guy. And then we'll do the limit as t tends to 0 of that guy. Now, there are different approaches to limits as t tends to a number. They're very similar to what you did with the infinity ones. The first one is, well, I wouldn't really call it brute force, but it is similar. Don't you just plug a number in, and if you get an answer, that's what it is. So an example of that happening would be this one here. Wouldn't the answer to this just be e to the power of 0? Would you agree? The limit as t tends to 0 of e to the power of t is just e to the power of 0, which is the number 1. Sometimes you have to do L'Hopital's rule. And if I plug in 0 here, I get 2 zeros as 0. And if I plug it in here, I get the sine of 0 as 0. And 0 on the top divided by 0 on the bottom is bad news, because we don't really know what that is. It's another example, a different example of what's called an indeterminate form, right? Infinity over infinity was one example, but 0 over 0 is another. So what you do in L'Hopital then is you differentiate the top and you differentiate the bottom with respect to t, and you then find the limit as t tends to 0 of that. But this is better, because isn't the top just 2, and isn't the bottom the cosine of 0? But what number is the cosine of 0?
1.
So that's basically 2 over 1, so now we've got 2. And the limit as t tends to 0 of tan t. Can we just brute force that and plug in 0? Yeah. Won't the answer just be the tan of 0, which is what, 0? And there's our limit. So if you want to find the limit of a space curve, just find the limit of each piece totally independently of each other, right? The answer to this has no effect on the answer to that, right? That's what I mean by independent of each other. Are we good? Now, I'm not going to do all of the other questions, but I am going to show you bits of them that cause people trouble. So imagine I had to find the limit as t tends to 0 of t to the 4 natural log of t. Well, if I try brute force, I get 0 times the log of 0, which is negative infinity, so that's bad news. But I can't do L'Hopital yet, because this fella isn't a fraction, and doesn't L'Hopital need a guy on the top and a guy on the bottom, right? It needs a fraction. So we do a little cheat. What do you think you call t to the power of 4 when you bring it downstairs?
T to the negative 4th.
Now, that's a very artificial looking fraction, but I don't care that it's kind of weird looking. Don't we need a fraction if we're going to do L'Hopital? Because that's pretty much all we've got, isn't it? You can plug in the number and you get the answer, or you can use L'Hopital, right? You don't, right now, you don't have any choices apart from that. So now I can do L'Hopital, and we'll see what that looks like. Well, if you differentiate a log, you get 1 over t. And if you differentiate this guy, you get negative 4 t to the negative 5. And this, somehow or other, we got to make it look pretty, right? We've got to do style points on it. Right, I'm going to call it 1 over t. This fella here is a bit messy. I'm going to keep the negative 4 there on the bottom. But won't this guy come upstairs and become t to the 5? Are you happy about this and that and what I did? I only moved one piece, that t to the negative 5 upstairs. The reason I did this, and I put an infinity there for some reason, the reason I did this is because I can now tidy it up a little bit. They cancel and you get that. So that's the style point version of what that ridiculously looking ugly fraction, right? That guy is in fact him. And now I can, whoops, I can do my brute force. Isn't it basically just 0? So we can do brute force. We can do L'Hopital. There's one technique. My next example is going to show you, and it's called the conjugate method. Now, for such a weird name, even if nothing else works, does that weird name stick in your head? Oh God, yeah, I remember there was something called that, right? The conjugate method is typically used when there is square roots involved and you can't get the answer with brute force. If I plug 0 here, I get 1 take away 1, which is nothing. I get nothing, 0 over 0. I won't be able to do L'Hopital on that. Well, technically I could, but it wouldn't help me. What happens when you differentiate square roots? Don't you get even uglier square roots? And that's the problem. Square roots and L'Hopital do not play well. L'Hopital works really good with t cubes and e to the t's and sine t's and things like that. Differentiating them is not an issue. They tend to differentiate quite nicely, right? But square roots of anything, especially square roots in the bottom, which are even worse. If you try to use the L'Hopital technique, you just get an uglier fraction that you still don't know the answer to, right? So we need this new guy called the conjugate method. And what you do here is a really sneaky piece of algebra. You multiply this fraction by a special version of 1. It's called the conjugate. And it's the same guy that has the square root, but with a plus instead of a negative. And this is called the conjugate, hence the name. Now you might think, how on earth is that going to make anything better? Well, let's find out. The bottom is just basically that. Right? Two things in the bottom multiplied together. Now, if you take this guy and you multiply it by that guy, right? So forget everything else and just focus on that. Do you recognize that when you multiply that out by foiling, something remarkable happens? Actually, kind of two remarkable things happen. The first one is, won't you have to do this square root times itself? So no more square roots. The second remarkable thing is, won't this guy cancel out that guy? So there's no more square roots again. And then don't you just finish with that? And then you tidy it up a little bit. And then you say, oh, I wasn't expecting that. Can you see something nice happening here? Cancel. Remember to leave a 1 behind. And so what the conjugate method has essentially done, it's took this ugly fraction that when we plug in 0, we get 0 on the top and 0 on the bottom, to a slightly nicer fraction that has this property. When you plug in 0, you get numbers. So if this was one of the 3 pieces that you had to find the limit of, wouldn't the answer for that one be a half? Do you feel comfortable about the 3 techniques? Plug in the number, get the answer. L'Hopital, or at least make it L'Hopital if it doesn't already look like it. And lastly, if you see some square roots, do the conjugate method. We good? Right. I'm not going to do these questions, but it is a very visual kind of thing. So let's just quickly have a look at the homework questions. Right. Are you looking? I hope you're looking at these guys here, right? Let's. If that answers one, shoot in space. Ah, well, it's my questions. It won't matter. Plug it in, L'Hopital, plug it in. Plug it in, plug it in. Can you see you're going to have to do that ugly fraction version? What do you think you might be doing with the 6e to the t minus 6 over t guy? You won't be able to plug t equals 0 in. Agreed? So what can you do instead?
L'Hopital?
L'Hopital, yeah. Do you recognize the only conjugate question, which is basically the one I did? And that one there, although it looks ugly, isn't the answer just 5 because you can plug in the number. So I would assume then that we feel pretty comfortable about those questions, right? So somebody says, find the limit of this space curve. We'll do it, right? We'll find the limit. No. Keep myself on track. Are you not amazed by how organized I am today? Do you see what a day off can do for me? Yeah. Okay, so here goes. Not that you're allowed to have a day off to be organized. You just ain't allowed. Remember that saying, which you almost have lived through? You do as I say, not as I do, which is what your mum or dad would tell you. Remember? True story, because I'm drifting and it's in my head and I'm homesick. My dad smoked like a chimney. He smokes coal miner, go figure. You'd think that's the last thing they should be doing. But he used to smoke cigarettes, and after that he went to the pipe. But my dad was very authoritarian, right? Definitely the old school. And my dad, you weren't allowed to smoke. He could smoke, but you weren't allowed to. Couldn't smoke a cigarette, couldn't smoke a pipe, couldn't do anything. I had married sisters who were 30 with 3 kids who smoked cigarettes. None of them do now, but did then. Who wouldn't do it in front of my dad. He'd inculcated that don't smoke in front of him. He was yeah, he had other rules. He didn't mind me drinking. Drinking, fine. Just don't smoke. You know, weird logic, you know. Okay, I was legal. He didn't like you drinking before you were legal, but he had no problems with it. Strange. And God, now I've got a joke in my head. I am drifting. Okay, I'll make it quick. You ready? Arkansas joke. What's the difference between a divorce and a tornado in Arkansas? You have to say, I don't know.
I don't
I
know.
don't know.
There isn't a difference. Both ways, someone's still going to lose a trailer. Okay. Do you know that the toothbrush was invented in Arkansas? And do you know how they found out that the toothbrush was invented in Arkansas? Because if it was invented in any other state, the toothbrush would have been called a teeth brush. Kathy's
okay, I get it.
Kathy is trying not to laugh at that one. Come on, Kathy, that's a good one. Are you shaking your head?
I always shake my head at your jokes.
Every single one of them. God, you must have a sore neck by now. Okay,
Exercise.
It's good for you. Right. Okay, let's move on to topic 2. How to find the domain of a space curve. Well, if I gave you a function like f of x, and I told you it was x squared plus 1 over x minus 2, when we talk about the domain of a function way back in Math 141, the domain would really be in English all usable values of x. Agreed? Now, when you're doing that, would you agree that this function here is totally fine, except for one value of x that is a bad idea? Right. So the domain in this case would be what? Every value of x except for 2. Great. Now you can write that down in 2 ways. One of them is what's called set builder notation. So you basically say the set of all values x such that x does not equal 2. And that notation is called set builder notation. Does that ring some bells? I know 141 was a long time ago, but You kind of remember it? Right. You could also give the answer in interval notation, in which case you would go something like that. And when it's written this way, it's called interval notation. So if I said to you, what's the domain of this function? You could say the domain was this. Right. Or you could say, in interval notation, you could say the domain was this. So far, so good? Right. Now, there seems to be a kind of analogy thing going on here. What do I mean by that? That we seem to be doing the same thing that we would have done. We just like do it 3 times, right? You know, like we find the limit 3 times. We find the derivative 3 times, right? We find the integral 3 times, right? We're going to do something a little bit different, but not too far away. Imagine this is a space curve and I want to find its domain. And this particular space curve is square root of 25 take away t squared. E to the power of t. And 1 over t minus 6. So there's our 3 functions, essentially. Now, when you talk about a space curve, the domain becomes all usable values t, right? So that's pretty similar. But here's where there is a bit of a difference. You take each function and you figure out, using interval notation, what its domain would be. Okay, so if you were looking at the square root of 25 minus t squared, would you agree that you can only use values of t that make this thing positive or 0? Right, so its domain would be that. Now, if you actually put that into a kind of graphing calculator, can you just trust me that it ends up being only values between 5 and -5? So that's what the domain would be if this was just my function. Right, that's my first function. Right, my second function was e to the t. Would you agree that e to the t doesn't have any problems? Everybody works with e to the t. So in that case, its domain is all of real numbers. And in interval notation, we would write that. And then my third example looks like this. Would you agree here that the domain is, I'm just writing it that way because it's easy to write, don't use 6. Now here's the problem. A space curve doesn't have 3 domains, it has 1 domain, right? And if you're talking about all usable values of x, don't you have to take into account any of these restrictions and put them together as a package deal, right? Now, this one here really doesn't bring anything to the table, so I could pretty much ignore that one, right? According to this, you must use numbers between -5 and 5. And according to this, you're not allowed to use 6. Now you put that package deal together, what would the restrictions be? Well, the domain here would be use everybody from -5 to 5. Now, why does that work? Well, I'm not going to use 6 if I only use numbers between -5 and 5. If I can use anybody I like, I'll use anybody I like, and I have to be between them. Do you see that that's what the package looks like in this case? Now, let me change one of the restrictions. See this guy at the end? Let's suppose that it was t take away 4. Then wouldn't this be you can't use 4? Well, that will change this answer a little bit. Instead of all the numbers between -5 and 5, it now becomes all the numbers between -5 and 5, but can't use 4. Now in set builder notation, that's a bit clunky, but what you would do is you would do this. Does that make sense? So when we are looking at the domain of a space curve, we are looking at a combination of 3 separate domains being put together as a package deal. And the way you know you've done it right is that whatever your interval is, shouldn't it work in all 3 situations? So if one of them says t has to be bigger than 2, and another one says t has to be less than 10, when you put them together, doesn't that mean t has to be between 2 and 10? Right, that kind of package deal. Right. So let's look at some choices here. This one is like question 5. And we're being asked to find the space curve for this fella. And it's a t take away 2, t plus 2. It's a sine of t. And it's the natural log of 41. Oh, yeah. I'll make it 4. 4 take away 2 squared. No, 49. I don't want to change the question too much. Okay, this is what my working might look like. Although some of this I'd probably do in my head. Would you agree for this fraction, just don't use -2 and you're fine, right? So for this fraction, the domain is everything, don't use that fellow. What would the domain be for the sine of t? What would the domain be for the sine of t?
-1.
You're thinking of values. You're thinking range. Domain.
Would just be infinity.
Yeah, anything you like, from plus to minus infinity. Now, the natural log of 49 take away t squared. That is not good. You have to know a little bit about the log function. It's very, very similar to the same restrictions that square roots do. Do you know logs can only have positive numbers inside them? Just like square roots can only have positive numbers. So a log equaling this, that's the restriction. Now, do you notice that I don't allow 0 this time? I would if it was the square root of 49 minus t squared. Now, if you take this guy and you sketch him, it's not difficult to be shown that it only takes positive values between -7 and 7. Now, -7 and 7 with curved brackets around them. Remember, curved brackets mean you can't use the end numbers, which is why greater than 0, right? Now, I want to put this together. You can use anything you like as long as it's between here and here and it's not that guy. That's probably how I would have said it in English, right? Pick any value of t you like as long as it's between -7 and 7 and it's not the number -2. When you put that package together, then that's what your answer would look like. Does that make sense? Any questions about that before we move on to the next thing in our list? Are we good then? So if you want to find the domain of a space curve, you're really looking for usable values of t. Now the third one's going to be really quick. It's saying sketch a space curve. So hopefully I've still got this thing on my screen. Where are you? Oh, here we go. So we have already on Canvas some software, and we kind of looked at it last time. So you've got a bunch of questions, 6, 7, 8, and 9. Plug them into this CalcPlot 3D guy, right? And put the X guy there, the Y guy there, and the Z guy there, and
We
there he
cannot
is.
see what you're doing.
Let me try that again. There, can you see him now?
There we go.
There you go. So plug it in here. Look at your guy. Get him orientated a little bit better. Right, X going this way, Y going that way, Z going that way. And you will have 4 pictures typically, and you pick the one that looks most like that guy. So your life's pretty easy, right? For those homework questions. If you feel brave about it, try and guess which of the 4 graphs it's going to be just by looking at the equation of the space curve. Good luck. You might get it. And that's all I want to show you about that one. So that section's nice and fast. Hopefully. It's kind of fun. I like playing about with that piece of software. So we've done that one. Right, our next one. How do you find the equation of a space curve? And there are 2 versions of this. You're going to be asked to do it when it's a line. And then you're going to ask to do it when it's the intersection of 2 surfaces. And the one that's an intersection of a line, I believe, is question 10, but let me double check on that. Yeah, so this guy is question 10. And the intersection of 2 surfaces is a version of it is question 11. Well, the only reason I'm doing line is for completeness sake, because you actually know how to do a line. You're typically going to be given 2 points. There we go, just randomly picking some guys. And you're going to be asked to find the equation. Let's phrase it the way they do. So it's find the vector equation and the parametric equation for the line joining P to Q. Okay. Don't you find the direction vector, PQ? Can you remember doing this when we did vectors, lines and planes? In this case, 2 take away 1, 8, 5 take away 3, 2, -7 take away that, -6. And then don't you use this point, I'll call them X1, Y1, Z1. And we call this, I think I called it ABC. And X then is X1 plus AT. Y is Y1 plus BT. And Z equals Z1 plus CT. In this case, it's 1 plus 8T, 3 plus 2T, and -1 minus 6T. So when they ask, oops, there we go. So when they ask for the vector equation, they want the guy that looks like this. And when they want the parametric equation, it's so similar, I'm not really sure it was worth doing. Can you see the notation is when you're doing it as a vector, you use the vector brackets and you do a little arrow above the R of t. And when you want to do it in parametric form, actually, if I was doing it in parametric form, I'd write it like this, but it's 3 separate equations. But evidently for WebAssign, they stick them all together. And you notice a little curve brackets notation rather than the vector notation. So if you're wondering which one's which, The vector one has the R of t and it has these brackets, and the parametric is that. But apart from that, aren't they identical? And the information is exactly the same information. So if I gave you a P and a Q, do you feel comfortable you could get the vector equation and the parametric equation? Oh, are we good with that one? Can we move on? Okay, got enough nods, I think. So the other type, which is question 11, is the intersection of two planes. I want you to imagine, because I'm really bad at drawing, that is an ellipse in 3D. Imagine it's a sausage. And I've got one of those, do you know the shapes that look like somebody's hat turned upside down? The one that looks like that. Can you imagine that the sausage and the hat intersect with each other? And when they intersect, do you know that you make a curve? Right, you make a sequence of points. That's the space curve that they want you to find the equation of. So if you put it in some 3D software, you might be able to picture it, but it's really an algebraic process. So this is their version. Z is equal to 4x squared plus 2y squared. So that's probably the hat one, right? Actually, it's the other way around. And the other equation is y equals 5x squared. I could actually draw y equals 5x squared. Won't it look like a big happy face going like this? You know, a curved piece of paper. So can you imagine a curved piece of paper intersecting with a hill kind of shape? How do you get the parametric equation? That's the problem. And this is how you do it. One of your two equations, in this case it happens to be equation 2, but it might be equation 1. But one of the two equations will always have two variables. Once you've found the one that's got two variables, in this case y equals 5x squared, make x equal t. Why is that useful? Well, that's because I can now tell you that y is 5x squared, so y is now 5t squared. You see, I've already got two of the three. How do you think I'm going to get the parametric version of z? I already have, yeah, I already have x and y. So z is 4x squared plus 2y squared. Z is going to be 4 lots of t squared plus 2 lots of this guy squared. So it's going to be 4t squared, 25 times 2 gets you 50, t to the 4, and there's your z. So if you want the parametric equation, it's t, comma, 5t squared, comma, this guy. A little bit of a cheat, but it works, doesn't it? As long as the information has one equation with two variables. Now, in this particular example here, y was equal to 5x squared. Can you imagine a totally different question where it might have said z equals 4y cubed? Right? So if this had said, different question, z was 4y cubed, just for argument's sake, make y t and z then can be 4t cubed. Do you see how you always get 2 for the price of 1? Now, once you've got those, won't you be able to figure out who the other letter is, because equation 1 can be used with substitution? You see, that's my strategy for solving that question. Are we good with that? You only get one homework question, and that's very similar to the one you're going to see.
Could you explain one more time how you get the first variable?
T. Well, I always pick, when you look at this guy here, make him, so make y t. Now, once you decide x is going to equal t, y is 5x squared, y then becomes 5t squared. Another question. Suppose you got z equals 2x cubed plus 1. Right? You have another equation up here, I don't care what that is. But you got this one. Make x equal t. Make z 2t cubed plus 1. Do you see I've already got 2 out of the 3 answers? Now, whatever's up here, you know, I don't know what it is. X plus y plus z equals 9, right? Whatever is up here, don't you replace the x with t, the z with that, and then solve for y, and that'll be what y is in terms of t, and that should finish your question. Does that help? Great. Okay. And they have to do it that way, or else the question's really not possible, right? If they give you 2 equations and they both have x, y, and z in it, you know, algebraically, that would be a difficult, if not impossible, process, right, to come up with an answer. Okay, so yeah, well, might as well get started. How do you find the points where a space curve intersects another plane or another space curve? Let's do a space curve, which is going to be t squared 2t minus 1, and intersects with some kind of plane. So what kind of plane will I have? Let's suppose I have the plane x plus y plus z equals 10. I'm trying to make my life easier. This space curve is going to meet up with this plane. So if you imagine this space, the plane like this, right? And the space curve might look like this. Gotcha, dotted line, dotted line, dotted line. Gotcha again, and travels on. So can you imagine that it is possible for a space curve to intersect any surface, in this case it's a plane, in more than one location? So what we're looking at right now is the process by which you would solve that problem. And we've already seen the solution when we did lines intersecting with planes. Can you remember how you go about solving it then? What do you do? How do you use this and this together?
Would you just plug in each of the functions and then find t and then plug t into the equation?
You nailed it. Exactly what you just said. Word for word. Couldn't have said it better. Don't you substitute these x, y's, and z's, that's what you said, into this one, the second equation. And we'll find, hopefully, we'll find some values of t. Now, since this is random and I just did it, let me put a little proviso here. It might not work quite perfectly, so I have the right to change the question to make nice answers happen, right? So if we take x, which is t, and we add y, which is that, and we have 2t minus 1 equals 10, and I may change that 10 in a minute, I've got t squared plus 3t take away 1 equals 10. Okay, that's good. I don't like 11, so since I want 10 here, I would like this to be 4. And so to make this 4, I'm going to pretend that the question said 3 all the time, right? So I can now say t squared plus 3t take away 4 is 0. I can now factor it as a plus 4 and a minus 1. which means that there is 2 solutions. Now for t equals -4, you go back to the original space curve and you find its position vector at -4. So it's t squared, and 2t take away 1. And then you try it at the other location, and you get t squared, 2t take away 1. So basically you get a point with coordinates this fella and another point with coordinates this fella. So if my picture here was correct, can you imagine that might be the P and this might be the Q? We almost made it. I'm not going to do any more. The next one is it's ridiculous. And oh, good news for me. The book, the homework questions didn't come out pretty either. So do you remember that ugly one that I changed so it'd be nice? They had an ugly one as well. So see if it's an ugly quadratic that doesn't factor. Can't you just do the quadratic formula and tell me it's 0.12345? And that's actually, I'm looking at the answer right now, that's what they got, right? So it's okay to have really ugly answers. You know they're going to be ugly because it says round off your answer to 3 decimal places. So the minute you see that, you know it's not going to work as a pretty answer. But I think this is more elegant, isn't it? It makes it a little bit easier to see what the heck you do with the